Okay, so thank you, Professor Derson. So, afternoon, everyone. Today, I'd like to talk about the potential impact of causal inference on railway PHM, which, let me reset the timing here. That's it. Which is a topic that lies at the intersection of AI and causal inference as a main topic. The deep learning technology, mostly around language processing and computer vision because of the data we'll be dealing with, and the industry of predictive maintenance as an application domain, mostly focusing on the analysis of the mechanical degradation of assets. And I would like to start my talk from this angle, because these are the people I have in mind: maintainers and engineers, people whose job is to keep things working, put simply. So I come from the railway industry, and railway transportation needs to be reliable and safe. So in the context of causality, what could be the effect of exposure to danger due to potential failure? And you're probably thinking about accidents, right? So this is Paris, 1895, the historically famous derailment of the Montparnasse station. So this particular steam engine had an issue with the air brake system that was available at the time. And as a result of this catastrophic event, there was one casualty and a partial destruction of the infrastructure. However, this spurred the development of more effective braking systems. So fast forward 70, 80 years, modern trains, such as the ones we use today, equip what is known as a blended braking system, where two different braking technologies get smartly integrated. We have the friction brake on the one side and the dynamic brake on the other side. So we now have a counterfactual question. Would the former steam engine have stopped in time had it equipped one of these systems? And we can probably guess the answer to this question. The thing is that we now have a trade-off for these increase of effectiveness of the systems. We also have an increase in sophistication and complexity of the machines, which in turn makes the job of maintainers and engineers increasingly more challenging to troubleshoot the issues. Although it's true that nowadays we also have data to help us out. And with data, we can observe international standards such as this one, which break down the complexity of the problems into modules that can more or less tackle in isolation in order to increase the odds of project success and reduce the technical debt. And in the context of predictive maintenance, we're mainly focusing on three objectives, which are the detection of anomalies, diagnosis of the failures, and the prognosis as a forecast. So now the question is data all we need to succeed? It's a matter of fact that trains are better today than they used to be in the past. But the world is changing constantly. And sooner or later, we're going to face the out-of-distribution data problem that we typically have in machine learning environments. However, if we adopt the causal inference mindset, we will be able to introduce the interventional tools, change this world, and evaluate the impact of this change for the future. But to do so, we can no longer rely on the many dependence assumptions that come with machine learning solutions. We need to understand the dependencies that bind the different variables and their roles, be they confounders, mediators, colliders, and so on, in order to build a convincing case for applying causal inference to predictive purposes. And it turns out that maintainers and engineers have been dealing with topics for a long time, compiling and building what is known as the failure mode mechanism and effect analysis documentations, which is a set of documents that describe the problems from the very beginning, that's the point of incipient failure, until the system crashes. And it turns out that if we now reread these documents through the lens of causality, we're going to find the same fundamental concepts, because we can liken failure modes to root causes, mechanisms to mediators, and effects to outcomes, building a beautiful graph that we can exploit with the tools of inference. And if we do so, we're going to be better prepared for the next challenges in the industry. And we won't be misled with what some people know as paradoxes, which is simply the result of not knowing what's going on in actuality under the hood. And here I'm just borrowing the typical Simpsons paradox. I will try to relate what is going on between two variables, cost and maintenance. So if we have the data for these two variables, we will clearly see a positive correlation between them. However, this is misleading. If that was the truth, we would be out of business because everybody would be trying to minimize their cost. Nobody would do any maintenance. But if you do that, we all know that the assets will eventually degrade, break down, and their availability will plunge. This is not what we want. To correctly read what's going on, we need to take into account the confounding effect of the age, the asset, or the fleet. And if we do so, we're going to change the trend of the association, correctly reading how negative they are, which in turn creates a business case for predictive maintenance. So investment in maintenance always drives the cost down regardless of the age of your assets, which is more advantageous than the corrective approaches that only fix the things that break and the scheduled approaches that develop maintenance plans at the beginning of the project without taking into account any data. And with all these, we can then see the many emergent properties of complex systems, such as the ones we typically deal with in a railway environment, which, like in that causal hierarchy that was originally defined by Judea Pearl as the godfather of causal inference. So down at the bottom, at the micro level, we see the misleading associations that we see in the observational data. And we know we have to climb the ladder of abstraction by adding knowledge, developing know-how to gain understanding about what things are really going on under the hood. And only if we do so, we'll be able to make educated guesses about what happened and correctly speculate what's going to happen in the future, which give rise to those interventional and counterfactual layers in this hierarchy of complexity. So in this talk, we're going to review two illustrative scenarios where these kind of things happen. And I really like this word, scenario, because it clearly describes what we are going to do, because this is typically defined as an outline of potential events, which in turn describe very well the kind of data that we're going to deal with. Because in terms of potential, those potential as an adjective will enable us to deal with both factual and counterfactual outcomes. And in terms of events, and specifically the relationship between events, that's the proper way to describe causality, not as a relation between properties or states, but events. And if we follow this description of the environment, we're going to create a sound philosophical space for the exposition that follows. So the first of these scenarios is in the field of linguistics. So linguistics is a topic that clearly exhibits this hierarchy of complexity. So over the morphology, the syntax, semantics, pragmatics, we find the interesting concept of the textual entailment, which is a directional dependence between two pieces of text. And this is what we liken to a causal relationship. And this is very relevant and useful for the industry of predictive maintenance because we have return on experience data, which is a data set that describes the problems that the staff find on the shop floor. And they also report the context and after the investigation, they also include their root causes and the solutions that were introduced to solve them. So in this scenario, the goal is to design a system that, given the description of the problem, is able to diagnose its root cause and is also able to advise the likely solution. So to do so, we first need to acquire the data and manipulate it. The first thing we realize is that we have variables with different types. So the first thing we have to do is to standardize that representation. So we here suggest using categorical representation. To this end, we utilize a modern NLP approach, making use of the embedded representations of these LLMs, these large language models, and the dense vector spaces. So specifically, we suggest using the bird topic approach. So initially, we get a sentence bird model to project the text into high dimensional dense vector space. We then reduce the dimensionality of that space with UMAP, and we finally quantize that reduced space with HDBSCAN, and finally apply the labels on the most relevant clusters. And then we have this uniform categorical representation, which enable us to build a model. Specifically, we target a generative probabilistic model, taking into account the different variable relationships that you can see at the top of the slide. Once we have this in place, we can then train a Bayesian network, which focuses on learning that joint probability function, which factorizes as is shown here, which makes it very explicit the decoupling between the different independent causal mechanisms. And once we have that learned model in place, we can then start implementing the different objectives. The first of which is the root cause analysis. That's a diagnosis function. So in this case, we're going to estimate this function by taking or by computing the observational conditional probability that's given us a ratio of marginals. And then the second objective, that's the estimation of the solution. We do that by building an interventional function, which is that objective. In this case, we need to take into account that we have the confounding effect of the common context and the common root cause. So we have to adjust for the contribution of these two confounding variables. And once we do so, we get a numerical representation of the solution, and we can then generate the outcome, which is the advisory. And in this case, we synthesize text, because that's the kind of interface that we are targeting. And to this end, we make use of a generative AI function, including a second LLM. In this case, we suggest using a Llama 2 model and some smart prompting. In this case, we pick examples from the return experience dataset that also show a category that matches the one that we predicted. And we also give some instructions to give structure to that outcome that we intend to generate. As a specific example, we report this return on experience record where the staff wrote that they found an issue with a mechanical brake. And if we apply the model, the approach that we're suggesting here, we will get a ranking of potential root causes. And we say that the leading one at the top, that's the part that's physically damaged, matches the ground truth that we have in the return on experience dataset. With regards to the generation of the solution, we see that the ground truth text that was reported is a bit cumbersome. So the staff got into the details of how they downloaded the data from the brake control unit, and then they did some experimentation with the isolation of the brake and so on. However, the kind of solution that we can generate with the approach that we propose is more concise. It provides a series of bullet points and a concise description for each of the potential solutions that are going to solve the problem. And what we see here is that in all of these solutions, the system advises to replace something. Given that we know that we have a part that's physically damaged, like it or not, we will have to replace something at some point. So as a conclusion, with the kind of approach that we are proposing here, we do not only get the correct diagnostics, but we also get more informative solution advisory. So with this, I will conclude that first scenario. The second one has to do with subsystem event logs, which is the kind of environment that we have on a complex machine, such as a train, where you have different subsystems distributed all over the space on the train, which generate events in time. And there's some other machine that snips that backbone network of the machine and logs all these messages. And this is something that reminds me, in a sense, of Conway's game of life, because in the end, in that environment, you have a set of very simple rules at the bottom. But once you start putting different units at the same time, then interesting patterns emerge. And this enables us to gain some predictive power. And with this, we can then apply the high-level cause-effect rules in these multivariate time series environments. So we initially target the detection of anomalies through the point of incipient failure, and we diagnose the root causes. But in this case, we're going to deal with the counterfactuals because we're interested in the individual features. So we transform the data with some kind of signals. We get these QR code images that resemble the game of life environment. Then we learn the structure that binds the different variables, and we learn a dynamic Bayesian network, which enables us to predict the failure. We track that evolution in time, which enables us to pinpoint the point of incipient failure. And once we have that, we apply the counterfactuals through the algorithmic recourse, which enables us to change the values of those variables in order to revert the anomaly. So they're telling me that I'm running out of time. So just to the conclusions, we get to the same kind of advanced advisory. We are mainly interested with the increase of the technology readiness level, mostly in the trustworthiness of the solution, and if you want to read some further details. Turns out that Barcelona, where I come from, has been a very hot spot for our students of causality. So we published 2 papers to the UAI and KDD conferences. So here are the links to the preprints and archives. So these are some of the topics that lie at the frontier of our R&D activities at Alstom. Thank you.